All right, so we're going to draw a slope field diagram for the differential equation dy dx equals 2x. So notice that in my picture, I've removed some of the dots that are in the diagram that I left for you on your page. Feel free to use this smaller number of dots. The dots I've erased, if you try to find the derivative there, it's like +8 or -8, and it's very difficult to draw a slope piece, a tiny slope segment with a slope of 8 and make that look different from a slope of 6. So we're going to use these points that I've left on this picture. So this is the first time, this is only our second slope diagram, but this differential equation has y as part of the function. So we're going to see how that changes the picture. So you can pick any ordered pair to start at. I'm going to start at 0, 0 just for old time's sake. If I plug in 0 for x and 0 for y, I'm going to have 2 times 0 minus 0 and a slope of 0. The slope is not always 0, it's 0, 0. But it is here, so I've drawn a teeny tiny horizontal line segment at 0, 0. And then, what's the best way to do this? You just have to organize this chart however it's going to work for you. Maybe I'll come do all the ones that have x is 0. So when x is 0, y could be 1 or 2 or -1 or -2. So when x is 0 and y is 1, I'm going to have 2 times 0 minus 1, which makes -1. When x is 2, I'm going to have 2 times 0, 0, minus 2, so -2. These guys are going to be the opposite. When I plug in 0 for x, 2 times 0 minus -1 will be +1. And 2 times 0 minus -2 makes +2. So I'm going to come to these 4 ordered pairs that I just filled in the rows for, and I'm going to draw in the teeny tiny slope segment. So at 0, 1, which is here, I need a slope of -1. That's 45 degrees going downhill. The slope of -2 should be steeper and also going downhill. At 0, -1, my slope should be +1, so that's 45 degrees going uphill, and then +2, like that. So now I'm going to draw the next part of this table. You're not required to make this table, but it's, I think, helpful to keep your work organized. So I'm going to try when x is 1. So 1, there are 5 points on my diagram where x is 1, so y could be, I'll start with the 2, 1, 0, -1, 2. So at 1, 2, my slope is going to be 2 times 1 is 2, minus 2, which is 0. At 1, 1, that's going to be 2 times 1 is 2, minus 1 is 1. Here, 2 times 1 minus 0 is 2. At x equals 1 and y equals -1, that's 2 times 1 is 2, minus -1, ooh, a slope of 3. And here, 2 times 1 is 2, plus 2 makes a slope of 4. So this is a little bit tricky to differentiate on your picture with a teeny tiny line segment. What's the difference between a slope of 2 or 3 or 4? It's not easy to do. They won't usually give you such fine differences between slopes on the AP test to deal with, but we can do this. So at 1, 2, my slope should be 0. At 1, 1, it should be 1. Then a slope of 2, a slope of 3, and a slope of 4. Slope of 4 should feel more vertical than a slope of 3, but that was tricky probably because my 3 is a little too steep. Nobody actually expects you to get out a ruler or anything and imagine what, 3 spaces up and 1 space over is. What you're looking for is slope segments that are steeper or less steep relative to the other slope segments on your diagram. All right, so let's try here. Getting these filled in. How about when x is 2? 2, 2, 2, 2. Y could be 2, -1, no, 2, positive 1, 0, negative 1, or negative 2. So when I plug in 2 comma 2, that's 2 times 2 is 4 minus 2 is 2. 2 times 2 is 4 minus 1 is 3. 2 times 2 is 4 minus 0 is 4. 2 times 2 is 4 minus negative 1 is 5. 2 times 2 is 4 minus negative 2 is 6. All right, so here we go. I'm going to draw in a slope of 2. Just trying to make that more than 45 degrees. Slope of 3 should be slightly steeper. 4 is steeper than that. 5 is steeper than that. And 6 is going to feel practically vertical. You can see why I didn't take us all the way out to where I had x equals 4. All right, so let's get the next. We're going to try the negative x's next. X, y, and m. So when x is negative 1, y could be 2, 1, 0, negative 1, or negative 2. So when x is 1 and y is 2. 2 times negative 1 is negative 2, minus 2 makes negative 3. 2 times negative 1 is negative 2, minus... Oh, I must have got that one wrong, because this isn't making sense. Let me try again. When x is negative 1 and y is 2, 2 times negative 1 is negative 2, minus 2 is actually negative 4. 2 times negative 1 is negative 2, minus 1 is negative 3. 2 times negative 1 is negative 2, minus 0 is negative 2. 2 times negative 1 is negative 2, minus negative 1, so negative 2 plus 1 is negative 1. 2 times negative 2 is... 2 times negative 1 is negative 2, minus negative 2. Negative 2 plus 2 is 0. So I'm going to start with this guy. When x is negative 1 and y is negative 2, I have a slope of 0. This is supposed to be negative 1. That's a negative 45 degrees. Negative 2 should be steeper, but still going downhill. All right, it's better if you hit the dot. I didn't quite hit the dot. And we have one more column to fill in here. One more time. Don't worry, on the AP test, they're not going to ask you to do something this long. We're just practicing. So here we go. What if I let x equal negative 2? There are 5 different y values in my picture. That's 2, 1, 0, negative 1, and negative 2. So when x is negative 2 times negative 2, sorry, 2 times negative 2, negative 4 minus 2, ooh, negative 6, that one's going to be tricky to draw. Negative 2 times 2, negative 4 minus 1 is negative 5, negative 4 minus 1 is negative 5. Negative 2 times 2 is negative 4 minus 0 is negative 4. Negative 2 times 2, negative 4 minus negative 1, negative 3. And negative 2, negative 4, plus 2, negative 2. All right. So probably you're seeing some patterns here. It's partly coincidence, but the way I've organized my tables, if I'm keeping the x value the same and changing the y's from their most positive to their most negative, my y's are decreasing by 1. So that helps a little bit. Here, I know I'm going to have slope negative 2. Slope negative 3 should be steeper. Negative 4 should be even steeper. Negative 5 is practically vertical. And negative 6 is going to be even more vertical. So we have here our first slope field diagram that has both an x and a y in the differential function. So notice how this slope field diagram is different from the one we made for y prime equals 2x. When we graph the slope field diagram for y prime equals 2x, it didn't matter what y value we used because y wasn't in the function, so we had up and down the same x value on the same vertical line, we had a bunch of parallel line segments. Notice that here, for example, if I'm looking here, those points all have the same x-coordinate, but they don't all have the same slope. So this is a case where the slope, the derivative, dy dx, depends on both x and y. Sometimes we'll have a differential equation that depends only on y, and in those cases, all the slope segments that are on the same horizontal line will line up. We're going to see how we use this in the next example.